Ostwald's dilution law. Ostwald's law of dilution. This is today's lesson. In this lesson, we are going to learn degree of dissociation and Ostwald's dilution law for weak electrolytes. Ostwald's law of dilution is applicable for weak electrolytes. Ostwald's dilution law is not for strong electrolytes. So, in this lesson, we are going to learn degree of dissociation and dilution law for weak electrolytes. So, let's get started. Firstly, let us try to learn degree of dissociation or degree of ionization. Degree of dissociation or degree of ionization, which is denoted by alpha. Alpha refers to degree of dissociation or degree of ionization. Let us suppose here solution of acetic acid. Its volume is 1 liter and concentration is 1 molar. In this solution, acetic acid ionizes partially in this way. Acetic acid ionizes partially to form acetate ion and proton in presence of water. Since acetic acid is a kind of weak acid, acetic acid establishes equilibrium state with its ions. Here, concentration is 1 molar. That means acetic acid is 1 mole here. Gram molecular mass of acetic acid is 60 gram. 60 gram acetic acid contains Avogadro's number of molecules. Simply, here acetic acid is 1 mole. Now, what is degree of dissociation? The amount of acetic acid from 60 gram that ionizes to acetate ion and proton. That amount from 60 gram is known as degree of dissociation. Again, here acetic acid, this Avogadro's number of molecules present here. Then, what is the degree of dissociation? The number of molecules from Avogadro's number that ionize to acetate ion and proton. That number is known as degree of dissociation. Again, the fraction of moles from 1 mole that ionize to acetate ion and proton. That fraction from 1 mole is known as degree of dissociation. Suppose here this is 1 mole from which this amount, a fraction of 1 mole of acetic acid that ionizes to acetation and proton. That fraction of 1 mole of acetic acid is called degree of dissociation. Here, this fraction from 1 mole. Here, fraction came from Latin word factus. Factus means broken. Factus is taken from Latin word. Now, what is degree of dissociation? A fraction of substance from 1 mole that dissociates into ions. That fraction is called degree of dissociation or degree of ionization, which is denoted by alpha. So, degree of dissociation or degree of ionization is equal to total number of moles in solution. Total number of moles in solution, from which number of moles dissociated in solution, that is number of moles dissociated in solution divided by total number of moles in the solution. This is degree of dissociation. That is, actually degree of dissociation is number of moles dissociated from 1 mole. Number of moles dissociated from 1 mole. This is degree of dissociation. That is simply moles per mole. Here, this is moles. Suppose 0.25. This is moles, not mole. When 0.25 moles of a substance dissociate from 1 mole, then this is degree of dissociation or degree of ionization. Moles from 1 mole. Now, Ostwald's dilution law. Suppose here, let us suppose a solution of weak acid HA. Its volume is 1 liter and concentration is suppose C mole per liter. Here HA, a kind of weak acid, that ionizes partially to form proton and anion. Here weak acid HA, initial concentration of HA is C moles per liter. This is initial concentration of HA when time is 0, and this is 0 moles when time is 0. But at equilibrium, what is the number of moles of HA? Here, degree of dissociation or degree of ionization of HA is alpha. Then at equilibrium, what is the number of moles of HA? As degree of dissociation of HA is alpha, then amount of alpha dissociates to form proton and anion. So undissociated HA at equilibrium will be this, as concentration of HA is C and protons alpha, anion alpha. Concentration of HA is C, so at equilibrium, hydrogen ion C alpha moles and anion will be C alpha moles. Here, alpha is degree of dissociation or degree of ionization that dissociates from 1 mole, and concentration of HA is C, so at equilibrium, number of undissociated HA moles will be C of 1 minus alpha, and similarly moles of proton will be C alpha, moles of anion will be C alpha moles. Now, according to law of mass action, as this is acid, so Ka, acid dissociation constant, will be product of the concentrations of the products C alpha divided by concentration of the reactant at equilibrium state C of 1 minus alpha. This is equal to C will cut this C, then here C alpha square divided by 1 minus alpha. This is equal to, we can write C alpha square, because 1 minus alpha is considered 0. The reason is degree of dissociation of weak electrolyte is considered negligible. Degree of dissociation is almost 0. So 1 minus alpha is equal to 1, because degree of dissociation is negligible, which is almost 0. So 1 minus alpha is equal to alpha. This can be considered, that is, acid dissociation constant is equal to C alpha square. Then alpha square is equal to Ka by concentration of the solution of weak electrolyte. Then alpha is equal to root over of acid dissociation constant 1 by root over of concentration of the solution. Here, this is constant. So, alpha is proportional to 1 by root over of concentration of the solution. This is Ostwald's equation, in which degree of dissociation for weak electrolyte is inversely proportional to the concentration of the solution. That is, when concentration is increased somehow by removing water, concentration is increased, then degree of dissociation will decrease. Again, when concentration is decreased by adding water, then degree of dissociation will increase. That is, we can say that with the addition of water, that is, with the decrease of the concentration, degree of dissociation increases, and with the removal of water, with the increase of the concentration, degree of dissociation decreases. Or we can write degree of dissociation is proportional to the square root of the volume. Degree of dissociation is directly proportional to the square root of the volume. That is, when volume increases with the addition of water, degree of dissociation increases. When volume decreases with the removal of water, degree of dissociation decreases. Here, Ka is equal to C alpha square. This is for weak acid. For weak base dissociation constant Kb will be C alpha square. This is for weak acid and this is for weak base. So, what is Ostwald's law of dilution? Degree of dissociation increases with the decrease of the concentration by adding water, and degree of dissociation decreases with the removal of water, that means with the increase of the concentration. Simply, Ostwald's dilution law is degree of dissociation is inversely proportional to the square root of the concentration of the solution, or degree of dissociation is directly proportional to the square root of the volume of the solution. Now, let us see applicability of Ostwald's dilution law. Applicability of Ostwald's law of dilution. This is applicable for weak electrolytes. Weak acids or weak bases. Number 2, at infinite dilution, Ostwald's law of dilution is not applicable. Because At infinite dilution, electrolyte ionizes completely. So, at infinite dilution, Ostwald's law of dilution is not applicable. Ostwald's law of dilution, which is proposed by Wilhelm Ostwald, German chemist and philosopher, proposed in the year 1888. Ostwald's law of dilution after German chemist and philosopher Wilhelm Ostwald. Let us suppose here solution of weak acid, acetic acid, volume 1 liter, concentration 0.1 molar. Then dissociation is 5%. Then what is degree of dissociation or degree of ionization? We know degree of dissociation or degree of ionization is equal to total number of moles present in the solution, 0.1, and here dissociation is 5%, that is 5 moles from 100 moles, that is 5 moles from 100 moles. Then what number of moles from 0.1 mole? This is number of moles dissociated in the solution and total number of moles present in the solution. This is equal to 0.05 moles per mole. This is degree of dissociation for this solution. Ostwald's law of dilution. Thank you for watching.